last time in chapter 16, we were talking about chapter 16 stuff. I want to see how many times I can say 16 in the sentence. So we were talking about some thermodynamic stuff. So obviously in this chapter earlier, we talked about delta S of the universe, which is the change in entropy for the universe is equal to the delta S of the system, plus the delta S of the surroundings. And remember, we could use this if it is positive, the reaction will be spontaneous. If it is negative, it'll be non-spontaneous the way it's written. We could calculate delta S of the system, like pretty much any type of thermodynamic sort of value. We take our final state minus our initial state, which essentially means in a reaction, we basically take the delta S of all of our products minus the delta S of all of our reactants. The delta S of the surroundings is affected by the enthalpy change, the delta H, and that is equal to minus delta H of the reaction over the temperature in Kelvin. And remember that they sort of work the same, are related to each other. So again, if we have sort of an exothermic situation happening under a sort of normal temperature situation, we would expect the surroundings to gain that energy, and we would expect the entropy or craziness of the surroundings to increase. And vice versa, if it's more of an endothermic process, we would expect the surroundings to lose energy, slow down, become more sort of organized and ordered. And we would see a decrease in the entropy of the surroundings. Remember, when we're talking about entropy, positive means more disorder, and negative means kind of less disorder along the way. And we cannot use either of those components alone, the system or the surroundings, to sort of determine if a reaction is going to be spontaneous or not. We do need to calculate the delta S of the universe. We can make a prediction, as we talked about, that if you, for example, produce more gas molecules than you started with, for the system, we would expect it to increase in entropy and become positive, or vice versa. If you end up with less gas molecules than you started with in a reaction, that's a little bit more order, and we expect the delta S there to be negative. We then got into Gibbs free energy, which is delta G, and that is energy available to do some type of work. And there's a couple sort of energy ones that we saw here, Gibbs free energy equations that we saw. Delta G is equal to delta H minus T delta S. And again, in this case, we do have delta H and delta S, which are in the same formula and also typically have different units. Again, this guy's typically in kilojoules, this guy's typically in joules. So once again, when we do use it, definitely in this equation, you got to do some type of conversion, either convert them to joules, keep them in, or convert them to kilojoules, so you're not off by a factor of 1,000. Temperature here obviously does need to be in Kelvin. We could use delta G directly to determine whether or not a reaction is spontaneous by the sign of it. If we end up with a delta G that's negative, we're going to hit a spontaneous reaction. If we have a delta G that is positive, it's going to be non-spontaneous. We also can calculate delta G like any other sort of, again, thermodynamic sort of property. We can take the delta G of our products minus the delta G of our reactants, just like we kind of do with any of the other ones by looking them up at the table. So again, a couple of different ways, and we'll see probably a couple more here in this chapter. And as I mentioned, I think last time, you definitely want to just maybe choose the ones most appropriate based on the information given to you in the problem as to, which delta G equation you might want to use. Obviously, if you have H or S given to you, then probably this one is a winner. If you have pretty much just the equation, then obviously this is probably the way to go in terms of looking it up. We also can make some predictions of spontaneity based on the actual signs of delta H and delta S, if they're positive or negative. For example, again, if we ended up with a positive H and a negative S, that negative on the S will turn this negative into a positive. And that would mean that this reaction really would be non-spontaneous at any temperature because of that. If we had a positive S and a negative delta H, The opposite would be true in this case. You would have basically a spontaneous reaction at any temperature because no matter what you do, in terms of the temperature, you will always yield a negative value of G. And there's some other combinations that we talked about as well. So again, sometimes you are asked questions like that, if this is positive, this is negative, would you expect it to be spontaneous? And again, we kind of talked through, I think, the different sort of four scenarios you could have with sort of this equation. Any questions on any of that stuff there? Seems semi-familiar. I don't know. Maybe we'll see. All right. So I think this is where we left off, I think. So let's talk a little about phase changes and free energy and what's happening. Because a phase change occurs at a specific temperature, and for example, solid to liquid is the normal melting point or freezing point of a substance. As we go from liquid to gas, that's basically the normal boiling point of a substance. That is an equilibrium process, right? So when you're exactly at that temperature where the phase change occurs, it typically is both phases in equilibrium with each other. So again, if you talk about water between solid and liquid, at exactly 0 degrees, you have ice crystals there. You got a little bit of solid, you got a little bit of liquid, so they're in sort of equilibrium with each other. I think we touched upon it earlier on in this chapter, but just a reminder as well, there is some heat associated with those transitions. The delta H of fusion is the energy required to go from solid to liquid or liquid to gas, liquid back to solid. Delta H of vaporization is the energy needed to do that transition of liquid to gas or gas back to liquid. And again, for water, roughly it's about 335 joules per gram. And for water, it's roughly 2260 joules per gram. That's roughly 6.02 kilojoules per mole, roughly about 40.7 kilojoules per mole here. And those are the heats of fusion and heats of vaporization, for example, for water. Reminder again that if you're not dealing with water, you would have different numbers per those values. You would also have different melting point temperatures, boiling point temperatures. If it's not, water, they would have different temperatures and those types of things. The energy required to do that transition again is the same value regardless of which way you're going, but the sign is different whether or not you're going one way or the other. As we go from solid to liquid, that's an endothermic type process. So that would be, for example, positive 335 joules per gram if you're going from solid to liquid. If you're going from liquid back to solid, you have to release that amount of energy. So it would be negative 335 joules per gram, again, in an exothermic value. Remember, energy that is negative, right, is exothermic, positive, endothermic type situation. So we can also calculate the entropy change for things like this. And again, because it's at equilibrium, if we took our delta G equals H minus T delta S, at equilibrium, delta G would equal 0. And if we're looking at this transition of liquid water going into gas, we can rearrange this equation up here and actually solve for the delta S, and that would be T delta S is equal to delta H. And then obviously dividing this to the other side will give us this equation. Now, if you remember earlier, we talked about the delta S of the surroundings, and it looks exactly like what you get here when you rearrange the equation. The main difference here is, if you remember, I talked about the negative sign. So if you're doing this rearrangement here, this does not have the negative sign. If you're calculating the delta S of the surroundings, it'll look exactly like that with the negative sign. So you want to be careful. Very common mistake people make is kind of insert the negative where it shouldn't be. And in this situation, there should be no negative because we're really just rearranging this equation here. Now, to do this transition, we would need the delta H of vaporization, and that is the 40.79 in this case, and that is the delta H of vaporization. This is 373, which I believe is 100 degrees Celsius. That's the normal boiling point here for water. That is when that happens. And if we do that, we will end up here for our sometimes referred to delta S of vaporization. The entropy of vaporization, 109 joules per gram. That is a positive number, which also makes sense based on what we were talking about with entropy. We're going from liquid to gas. That's a lot more disorder, which means we should end up here with a positive value for our delta S of vaporization. Any questions on that? By the way, if I was doing sort of the opposite transition here, if I was doing the water going from gas back to the water and liquid, this is condensation, right? Is what is going on here. And if I were to calculate my delta S, say, of condensation, that would be still my delta H over T. The only difference here is my heat of vaporization would not be a positive number. It would be a negative number. And it would be negative 40.79 as it is exothermic over my 373. And I would end up in that direction with a negative 109 joules per Kelvin. And that also makes sense if you're going in that direction, because again, you're going from gas, which is crazily flying around, to a more ordered state in liquid. So here, again, the entropy would be the same, just the sign here would be different, indicating that we are increasing the order in this case. Questions on that there? Obviously, you could do similar calculations for entropy of like fusion, right? The transition from solid to liquid. You would just use the heat of fusion, the delta H of fusion for, say, water or whatever it may be, in place there. And the temperature would be different. It would be 0 degrees Celsius, which would mean obviously it would be 273 Kelvin, right? If you're doing more of a fusion type of calculation. Any questions? So let me try this one. The enthalpy of vaporization for mercury is 58.5. Normal boiling point is 6. Okay, so taking a look at this, our enthalpy of vaporization is our delta H of vaporization, which equals 58.5 kilojoules. So here we are doing again the transition of liquid to gas in this case. Again, this is going to be an equilibrium type of situation, which means if we take a look at our equation, that will turn our delta G into 0. We could again do our sort of rearranging of this equation here and solving for our delta S, maybe not the T, delta S. And again, divide that way. And in this particular case, it did give us temperature in Kelvin. As you can see, these values, again, are different than the ones we see for water. So again, if you're not dealing with water, they will have different values for delta H of vaporization and boiling point temperatures. We'll put it in here, 58.5. I'm going to times it by 1,000 just to convert it into joules. You don't necessarily have to if you don't want to. The only difference is your answer will be in kilojoules if you did not convert it. So we'll go 58.5 times 1,000 divided by 630. Going to get me about a 92.9 joules per Kelvin as my entropy of vaporization. And again, if you left it for in kilojoules, you have 0.092 as well. Again, this is going to be a positive value for my entropy of vaporization, as we would again expect as we're going into the gas phase and creating more disorder. Once again, if we were kind of doing the condensation version of this calculation, everything would be the same except the sign on our delta H vaporization would become negative in that case, turning our delta S into a negative as well. Any questions on that one there? So it's been too long since we talked about equilibrium, so let's tie that into here. All right, so I was talking about Gibbs for energy and chemical equilibrium, and we do end up with this equation here, which is the delta G is equal to the delta G naught plus RT natural log of Q. And remember that sort of when you see these little knots, this really does mean sort of standard conditions. And a reminder that when we're talking about standard conditions, that is, again, all the concentrations of their solutions should be all 1 molar. If it's gases, their pressures should be 1 atmosphere. So if you come across a problem where you're dealing with concentrations that are not 1 molar, or you're dealing with perhaps pressures that are not 1 atmosphere, then you're probably under non-standard conditions. And that's sort of what you can think of this first G as. This is going to be sort of our delta G under non-standard conditions. This delta G not here, if it was not given to you in the problem, you would calculate like normal. That would be equal to our delta G of our products minus the delta G of our reactants. And again, that would be the one you go to the table probably and look up the values and do products minus reactants. The R here is the gas constant. Again, it is the one that involves energy, so it is the 8.314. T is our temperature in Kelvin. And this is Q. And remember, again, Q is the same thing that we've seen previously. It is the reaction quotient, and Q is calculated the same as K. And that means that Q is basically equal to our products divided by our reactants, obviously taking into account the coefficients like normal, and calculate them. So again, you can kind of think of this as almost like the third equation that we see with delta G in it. And this again would be a situation where you'd want to use this equation if again you see you're not under standard conditions. So that should push you to sort of this equation. Now, if we do get to equilibrium or at equilibrium, a couple things happen. Again, delta G is going to equal 0. And if we're at equilibrium, our Q is no longer Q, it would be the equilibrium constant. And basically the top equation here reduces down to another delta G sort of equation. And this is delta G naught is equal to minus RT natural log of K. Again, normal stuff here. The R is still the 8.314. Temperature is still our temperature in Kelvin. And K is our equilibrium constant. So if you're keeping track, that's like 5 equations with delta G. And as I mentioned earlier, I would choose the equation that best fits sort of the information that's given to you. So if you have anything that says to do with the equilibrium constant, it's the one on the bottom here is the one to use. If you have anything again with non-standard conditions, the one on top. If you have an H and an S, is the one that we saw earlier that has both of those in it. Again, if you just have the equation, you're going to go products minus reactants. So again, you want to kind of tailor probably your delta G1 to the information that is in the problem and to use. Now, when we look at these things in terms of the equilibrium constant and delta G, they really should still make sense with each other. So what we know about a couple things is if I have a negative delta G, that means my reaction should be spontaneous. And if it's spontaneous, it should be heading to the product side. And because it's heading to the product side, I probably will have more products than reactants, which means I should probably have a larger amount or a big value of K in that case. Opposite is true. If I had a positive value for G, that would mean the reaction is non-spontaneous. And in that situation, you're heading towards the reactants, which should yield you a smaller value for K. So again, those things should agree with each other. And I say those are things you should think about as you're doing these problems because there are definitely parts of the calculation where if you miss like a negative sign, you will end up with the wrong value, especially if you do like the E of a number and it's supposed to be negative versus positive or positive versus negative. You will find yourself very different answers that you should have. But again, you should be able to kind of make those things agree with each other and recognize that, hey, I got a positive delta G, but I have a very big value of K. Those things probably shouldn't go together. And again, those are good ways to kind of think about it as you're doing these problems. Any questions on that there? Obviously, as well, if you have a K value that's equal to 1, it's pretty much going to give us a delta G close to 0. And then products or reactants may be favored in this case. So once you give this a go, calculate the equilibrium constant for the fall. All right, so obviously this involves the equilibrium constant, so grab the equation that has that in it. That's minus RT natural log of K. In this case, obviously R we have, which is our 8.314 joules per Kelvin per mole. Our temperature is 25 plus a 273 gets me a 298 Kelvin. And we are looking for K. So we got this, we got this. We do need to, again, look up in the table there and calculate delta G. And again, our delta G here going to be delta G of our products minus delta G of our reactants. In this case, we got 3 times 0 kilojoules, basically, for our O2, minus 2 times our O3 value from the table. Looks like 163.4 in this case. And that's going to get us here negative 326.8 kilojoules as our delta G. Now we have this, so we're good to rearrange here. Natural log of K, we're going to take both of these and divide it to the other side. Going to be delta G naught divided by RT. I'm going to not forget that there's also a negative there that needs to come along for the ride. Popping my numbers in here, I got minus 326.8. That's kind of like 32.6.8, but yeah, it's kind of close. Let's see. I give her that number there. There we go. All right, so 326.8. And once again here, I am going to multiply that by 1,000 to convert that into joules. And again, I'm not going to forget the extra negative that's there as well. So that's a double negative. And we're going to divide that by R, 8.314 joules per Kelvin per mole. Once again, this is why I converted my top number into joules, so everything cancels out correctly. Otherwise, you need to convert, obviously, R into kilojoules, so those units cancel out correctly. Temperature here, 298. That is going to get me something. 1,000, 8.314 at 298. Gonna give me a 131.9. I'm gonna E both sides here to get rid of the natural log. And that's gonna get me a K value of, we'll call it 1.9 times 10 to the 57 in this case. First off, any questions on that calculation? Now, again, we do see some things that do sort of correlate to each other. Here we yielded a negative delta G, which should tell us this reaction is spontaneous. That also means we should be heading to our products, which means we should have more products than reactants, perhaps, and we should probably have a larger value for K, and I say that's definitely large in this particular case. Yeah. Any questions on any of that there? What's that? Yeah, the value of delta G was negative, which means the reaction is going to be spontaneous. And if it's spontaneous, it should imply that this reaction is heading towards the product side. And because it's heading towards the product side, if we think about what that means in terms of our equilibrium constant, that's products over reactants. We probably should have a little bit more products than reactants, so we should have more larger value of K, which definitely that one should qualify, yeah. To solve for K. You couldn't in this case be if you're asking can you directly just kind of put this into the equilibrium expression? Is that what you're asking? Yeah, so in this particular case, there's no way for you to do that because you don't have any of the concentrations. Yeah, so if you did have concentration or something like that, and they were equilibrium concentrations, then you wouldn't actually need the delta G part of this. You could go right into it. But in this case, you had no information about sort of the concentrations of everybody, so you couldn't actually do it in this case. Yeah. Other questions? All right, so let's take a look at another one here. Delta G for the following is KSP, 1.7 times 10 to the minus 6. What is or calculate the delta G for this? Okay, so again, in this case, we got another equilibrium, so we'll go with the same formula here, equals minus RT natural log of K. In this case, actually, we got everything on this side. We got all that given to us, basically, so we could go right into it. So our delta G in this case would be minus Our R, which is again the same one, 8.314. Our temperature here, which obviously we need to convert to Kelvin, so we'll add a 273 to it, gets us 298. Natural log, in this case, we are actually given the K value. Doesn't matter, again, what type of K value it is. They're all the same. Doesn't matter what the little letters on the bottom are. So just kind of cleaning up everything here. We got natural log of 1.7 to the minus 6. We're going to times it by 298 and times it by 8.314. We're not going to forget about the other negative that's on the outside. And that basically will give us a positive 32,914. The units in this case are going to be joules based off of the R value here. Or if you want kilojoules, 32.9 kilojoules in this case. First off, any questions on that calculation there? Once again, we do see agreement between our K value, which is a small value of K, which would probably imply we don't have very much of a spontaneous reaction happening here. So that again goes with a positive value of G. So again, those things should really agree with each other, and it's sort of a good way to check yourself in a lot of cases. Any questions on that one there? All right, one last one perhaps here. The delta G naught for this reaction is 2.6 kilojoules at 25 degrees. In one experiment, the initial pressures of H2 is 4.26, I2 is 0.024 atmospheres, and HI is 0.23 atmospheres. Okay, so let's take a look. And in this particular one, a couple of things you want to obviously look at. We are given a delta G naught, which again, you may have to calculate yourself, may not always be given. We are looking for a regular delta G here, and the big thing is these right here, the pressures. And our pressures here are not all 1 atmosphere, which tells us this is non-standard conditions. And that should point you, again, really to the only equation that has really the two delta G's, sort of the non-standard standard one. We would want to use this equation here. Remember, it is a plus RT natural log of Q in this case. And again, it's really because of our pressures here, not all being 1 atmosphere, non-standard conditions. So like I said before, sometimes you are given the delta G not like we were in this particular problem. And again, sometimes you may have to calculate it yourself. R is obviously our constant that we used previously, our 8.314 joules per Kelvin per mole. We got 25 degrees there, which is going to give us a 298 Kelvin. So we are looking for this guy, and really the only thing we're kind of missing here is Q. And remember, again, Q is our reaction quotient, and it's basically products over reactants, just like we do with our K. So Q would equal, in this case, actually, these are pressures, so I guess it would equal the pressure squared of HI divided by the pressure of H2 and the partial pressure there of I2. So if we pop those numbers in for those guys, it looks like we got 0.23 squared divided by 4.26 and a 0.024. That's going to give us a Q here of looks like we'll call it 0.5174. Now we have pretty much everything there on the right-hand side, so putting all that good stuff in. We're going to go with 2.6. Again, I am going to convert it into joules because of my R, or again, you got to convert your R to kilojoules. It's really your choice. Plus, again, my 8.314, my 298, and my natural log, what I got there, 0.5174. All right, so kind of cleaning up to the right of the plus sign there, natural log of that whole number, 0.5174 times 298 times 8.314. That's going to get me over here on this side, negative 1632.5. Again, these would be joules at that point. So now adding that to our first number, 2.6 times 1,000. And we're going to add that to our negative 1632. That's going to get us here a 967 joules, or 0.967 kilojoules, depending on whichever way you went there. Question on that? Yeah. They do. So remember Q and K, they don't have units associated with it. So uh, technically, you kind of eliminate those units. And um, so really in these sort of calculations with the energy, you're really going to look at like your G and your R, those are going to kind of be where you're going to have those units. Yep. Other questions? Yeah. It would not. So just like we talked about with the equilibrium one, I mean, technically they do, but they don't really cancel out very nicely. So that's why we typically don't use units with them. So you can continue not to have to worry about the units here in this particular case. Like here, you would end up obviously with like 1 over, something like atmospheres or something like that. So um, just like normal, no units associated with those. Yeah. Other questions? All right, that is chapter 16. So we're just going to kind of get into a little bit of this chapter here and then we'll call it a day. Um, and we're also going to talk about a little bit more just basic redox. So this chapter is about redox reactions. It's about electrochemistry. Really, the main part of this chapter is really about galvanic cells, which are redox reactions. But depending, I guess, on maybe who you had for Chem 50, you might have did a little bit more or less of redox reactions or not, or balancing them. So just to make sure everybody's on the same page, we're going to kind of go over the basics of balancing redox reactions, identifying oxidation numbers and states like that, so that when we get into kind of the main part of the chapter, you obviously hopefully will know how to do that as well. So obviously, we're talking about redox reactions, which is really a big classification of reactions, which involves really one of the three reasons why reactions take place, which is ultimately here electrons being transferred. As you may know, there's really three reasons why pretty much most reactions take place. Either one of three things are happening, electrons are being transferred, you made a solid or you made water. Those are the big three of that's what's happening basically in this reaction. So when we talk about redox reactions, that is just regular types of reactions that you may be familiar with that are redox reactions, things like synthesis reactions, decomposition reactions, single replacement reactions, combustion reactions. These are all more specific classifications of redox type reactions. In terms of redox, what it means is really oxidation and reduction. And these things always occur together. So there's always somebody getting oxidized, there's somebody getting reduced. Oxidation has several meanings, and the one we use mostly in general chemistry is the loss of electrons. So somebody loses electrons, while reduction is somebody has gained electrons. Thank you. And sometimes people remember Leo the lion goes grr, loss of electrons, oxidation, gain of electrons, reduction. People nowadays are fond of the oil rig. Oxidizing is losing, reducing is gaining. Throw Leo the lion on the oil rig, he goes grr. You don't have to choose, just use all four of those things together and not have to pick or anything like that. So when we talk about these things and we talk about sort of when somebody gets oxidized or reduced, a lot of times what we look at is what's known as the oxidation state or the oxidation number of what's going on. And a lot of times, if you could identify, for example, for the element on the left-hand side of the arrow versus the same element on the right-hand side of the arrow, you could determine what is happening. Is it being oxidized or reduced? And a basic, simple way that you could really figure that out, pretty simple, is just a basic number line. And with a basic number line, there's usually positive numbers on that side and negative numbers on that side of zero. And the idea here is if somebody loses electrons, they actually become more positive as they would go from the reactant side to the product side. And that's because they now have more protons than electrons, right? So they become more positive. So if you look at the oxidation number of a species on the left-hand side versus the right-hand side, and it's moving towards the positive direction on this number line, that means that thing is going through oxidation. Vice versa there, in reduction, things gain electrons, which means they become more negative because they now have extra electrons. So if you look at the oxidation number state of a species on the left-hand side of the arrow to the right-hand side of the arrow, and it's becoming more negative and moving in this direction on the sort of number line, then that thing is going through reduction. So it's a very sort of simple way to sort of figure out, is something being oxidized or reduced. So for example, if you had iron 3 going to iron 2, in this case, all you have to do is go to the number line and go, all right, +3 on the left-hand side. So that's where my iron's starting over here. Right-hand side +2, that is moving this way, which is moving towards the negative side. And we would know that this guy is going through reduction in this case. So it's a very simple way to sort of figure out, what is being oxidized, what is being reduced when you look at it. Any questions on that there? So what we're going to really be looking at in this particular our chapter is a lot of electrochemical processes, which are really oxidation and reduction reactions that are occurring. And one of the nice things about that is if you could identify just what is happening with one thing, like this thing is getting oxidized, by default, usually the other thing is being reduced and vice versa. Now, the idea here is, as we'll talk about in this chapter, is as those electrons are being lost by one substance, they could go out and actually do some type of work, kind of similar to like when you put batteries in things. There's little wires in the battery compartment. It's really a redox reaction that's occurring. Electrons go out through the wire and power like your calculator or something like that and come back through the other way. And again, they're used to do some type of non-spontaneous process here. So if we have a reaction such as this, the oxidation state of anything in a standard state that is uncombined is 0. So the magnesium on the left-hand side here is 0. The oxygen, that is naturally how it comes. So its oxidation state here would also be 0. Remember that things really don't get charges until they hook up with each other. A metal and a non-metal to make an ionic compound is typically when that happens. And in this situation, my magnesium's group 2 with a +2, and my oxygen is a -2. So once again, you could use that number line if you're not sure what is going on. If you look at the magnesium, it started at 0 and ended at +2. It's going towards the positive side, and this is going through oxidation. By default, that would mean that this guy is going through reduction in this case. You could also do it for the oxygen. Oxygen started at 0 and ended at -2, which means it's becoming more negative here, and it is getting reduced in this particular case. So what's happening in this particular case is the magnesium is shuttling the electrons over to the oxygen, and we get our transfer of electrons, which is the basis of a redox reaction. This is also classified as a synthesis reaction and also a combustion reaction as well, because it has oxygen in it, is the way you can classify it. Now, when we deal with redox reactions, we oftentimes will break the overall reaction into two parts, one part being the oxidation half reaction and one part being the reduction half reaction. So in this particular case, if we broke this reaction up into its half reactions, and they're called half reactions because, frankly, they're half of the overall reaction that's taking place. We get our oxidation half reaction, which is magnesium, again, with no oxidation state or 0 to a +2 oxidation state, and it is giving off 4 electrons. And we know that this is the oxidation half reaction because our electrons are on the product side. So in an oxidation half reaction, your electrons should always end up on the product side of the arrow. Here we have the oxygen gaining those 4 electrons and forming 2O2 minus. And that is the reduction half reaction. And on the reduction half reaction, our electrons are always on the reactant side. They should actually never be on the same side of the arrow when you're writing half reactions, because the one thing that should always cancel out when you add these reactions together is the electrons. So the electrons should always cancel out. The idea here is however many electrons the guy that's getting oxidized loses should be the exact same number of electrons that the one getting reduced gains. So if we were to add this together, these two half reactions, the electrons are on opposite sides of the arrow, so they will cancel each other out. So anything that's on opposite sides of the arrow that's the same thing could cancel out or reduce down. And that leaves us everybody on the left-hand side stays there, and everybody on the right-hand side stays there. These are two ions, and we do end up with an ionic compound, in this case, two of the magnesium oxides. Now, you may be asking, why is it 4 electrons in this particular case? It is because there are 2 magnesiums, and each is going to lose 2 electrons. So that's a grand total of 4 electrons in your balanced equation in this particular case. Now, this is the way we add together simple half reactions. The only thing you have to worry about when you're adding together sort of simple half reactions like this is that the electrons are the same in both half reactions. If they are not the same number of electrons in both half reactions, you may sometimes have to multiply either one or both of the half reactions by a common number to get them to the same number. So for example, if I had 2 electrons in the first and 3 in the second, hypothetically speaking, I would need to multiply the first one by 3, the second one by 2 to get 6 electrons in each so that they are the same. And sometimes that happens in redox reactions when you're trying to put together your half reactions. You got to multiply it by a common number. By the way, we should expect this to happen in this type of reaction because magnesium is a metal and oxygen is a non-metal, and that makes an ionic compound. And when you have an ionic compound, metals are always the one that lose electrons, right? To the non-metals, they're always the ones that gain it. So in these type of reactions, like a synthesis reaction here, if you're making an ionic compound, your metal should always be the one being oxidized, and your non-metal should always be the one being reduced, because that's what happens when those two things sort of come together, right, to form an ionic compound. Questions on that there? All right, so that's what we just looked at. Here's again another example of a synthesis reaction, which is a redox reaction. And once again, if we look at our calcium, that is 0. Oxygen is 0 in terms of its oxidation state or number. Once again, when those two come together on the right-hand side of the equation, they are ions. So that's +2 and that's -2. So once again, we have a similar thing happening that we saw in the previous one. Our calcium is starting at 0 and going to +2 on the right-hand side, which tells us it's becoming more positive and going through oxidation. Our oxygen, again, is starting at 0 and ending at -2, which tells us it is going through reduction in this case. And in this case, we also agree upon that based on what we just said. Calcium is a metal, oxygen is a non-metal. So again, here, the calcium should be the one losing electrons, and our oxygen should be the one that is gaining electrons in this case. Again, we could write our half reactions here. This is going to be our oxidation half reaction as those electrons are being given off, so they kind of are on the product side, as opposed to our reduction half reaction, where those electrons, again, are going to end up on the reactant side. Once again, electrons should always completely cancel out. You should never be left with electrons once you add together some half reactions. And that gives us back, obviously, our overall reaction in this case. Now, another thing that sometimes confuses people is a reducing agent and an oxidizing agent. And if you're asked about a reducing agent or an oxidizing agent, that is a different question than what is being oxidized and what is being reduced. So oxidizing agent and reducing agents, different question than what is being oxidized and what is being reduced. Now, oddly, as it says there, our oxidizing agent is always the species that gets reduced. Now, you may be asking, why is that? And the reason for that is when it gets reduced, it has to gain electrons. And the only way for it to gain electrons is it has to cause somebody else to lose electrons, which means it's causing somebody else to get oxidized. So it is the oxidizing agent in this case. while our reducing agent is the species that gets oxidized. And same idea, because it gets oxidized, it means it's going to lose electrons, and somebody's got to pick up those electrons, so it just caused somebody to be reduced in that case. So oxidizing agents, reducing agents, what is being oxidized and what is being reduced, by the way, all of those things are always found on the reactant side of the arrow. Yeah, so all those things are on the reactant side of the arrow is where you find those things. In the previous example, calcium was oxidized, which means it lost electrons. So in that example, the calcium was our reducing agent. The oxygen was reduced, which means it gained electrons, which means in that previous example, the oxygen would be our oxidizing agent. So again, the agents are sort of opposite of the name as to how you determine them. Now, there is two other definitions of oxidation and reduction that we really don't use all that much in general chemistry, but you will use a lot of it in organic chemistry if you're going in that direction. If you are, I'm sorry, but we use that. I'm just kidding. So we know it's losing electrons. Maybe I'm not kidding. I don't know. We gain electrons here. So oxidation also definition is that something gains oxygen as it goes from reactants to products, or it can lose hydrogen as it goes from reactants to products. And reduction has similar definitions. It loses oxygen as it goes from reactants to products, or gains hydrogen as it goes from reactants to products in this case. So those are three definitions. Like I said, these definitions of oxygen and hydrogen are typically used a lot in organic chemistry because there's not a lot of metals and charges. There's a lot of non-metals involved. So sometimes it's easier to look at, did this thing gain oxygen or lose oxygen, or gain hydrogen or lose hydrogen? So for example, in this particular case here, if we look at the tin, it has oxygen on the left, but no oxygen on the right. So it actually lost some oxygen here, which is a definition of reduction. If we look at the carbon on the left to the carbon on the right, it gains some oxygen. So this guy is going through oxidation. This would mean that in this particular case, our carbon is our reducing agent because it's being oxidized, and that would be our oxidizing agent in this particular case. Now, in this particular case, because there was tin involved, you could actually use the tin to figure it out if you weren't sure. The tin in this case is +4 because oxygen is -2 and there's two of them. The tin on this side is 0. So if you went to your number line there, you could very easily see +4 is over here and down to 0, which means it's becoming more negative and is getting reduced in this case. So you could actually still do it here since the tin is there. But sometimes we do kind of look at these other definitions. And again, more so in organic chemistry, I think is where we do. Any questions on oxidation, reduction, all that kind of stuff? I think we'll lay it up there for today. I think you've had enough torture. All right.